Hi everyone. Since we do not have, we will not be able to have class on week 12, 13, and 14. So I will do a recording. This is a recording of a tutorial of chapter 6, right? So last Thursday, we have already completed the lecture for chapter 6, but we do not have the time able to complete the tutorial. So this is the video recording for the tutorial chapter 6. As usual, the questions are in Teams as well as in VLE. So please refer to the questions, and the final answers are all in the tutorial question. So this tutorial video is to guide you for the tutorial question, but as usual, I will not cover all the questions. I think we have about 4 or 5 questions. So I will leave about 1 to 2 questions for you to do it on your own. Okay, to attempt it at your own, and then based on the guidance that I will show for the previous question. Okay, so looking at the screen. All right, so before I go, let me just recap back. What do you learn in chapter 6? So chapter 6, we are dealing with non-isothermal reactors, meaning we're talking about reactors of which there are changes of temperature during the reaction. Okay, so that's the main difference of the interesting part of chapter 6. We are addressing reactor design when there are changes of temperature during the reaction. So as you can see, they will affect the design of the reactors, and so that's why we are introduced to a new equation. We call it as the energy balance equation. So this equation is correlating between the two important parameters, which is conversion X and temperature T. Meaning to say, let's say in your scenario, you know your desired conversion. You would like to find out what are the temperature to achieve this desired conversion. So this, you can use the energy balance equation, or vice versa. Let's say you know your reaction temperature, you would like to determine what is the conversion. So either I know X, I find T, or I know T, I find X. And subsequently, when you solve these two parameters, then we can find the volume of the reactor, which is mainly CSTR. Okay, so I think the chapter is not difficult, but as you know from the lecture previously, the equation can be a bit complex. It is a long equation, and the equation has sub-equation, and even the sub-equation may change according to the reaction. So that's the part that you have to really understand. Okay. So let us go to the very first question. So it says, given the irreversible non-isothermal liquid phase reaction as follows. Okay, so you know that this is irreversible, non-isothermal. Okay, so you know this is that reaction of which the temperature changes, means the inlet and the reaction temperature is no longer the same, and the reaction is between one reactant A and one reactant B reacting to produce 2C. Okay, so this is a stoichiometric coefficient. The reaction is carried out non-adiabatically in a flow reactor. So you learn reactions non-isothermal. We have adiabatic and non-adiabatic. Okay, so what's the difference? It's a very easy understanding. Non-adiabatic means you have to calculate Q. Adiabatic means Q is 0. Okay, so means non-adiabatic, you have heat supplied to the reactor, hence you have to calculate the Q. If adiabatic, Q is 0. Okay, so that's first information. So means in this case, we are supposed to calculate Q, right? So the next one, an equal molar of A and B enters the reactor at 343.15 Kelvin at the flow rate of 60 dm cube per second with initial concentration of A of 18.5 mole per dm cube. Okay, so from this one sentence, again, you can see there are few information that you have to understand. First of all, equimolar. Equimolar means initially you have unknown molarity of A and B. So we do not know how much is this molarity or the concentration, but we know that it is equal molar. So let's say you can assume it can be 2 molar A, 2 molar B, or 4 molar A, 4 molar B, but we do not know this amount. However, from this amount, you can know the mole percentage or the mole fraction. meaning it will be in terms of percentage or composition, you have 50 mole percent A, 50 mole percent B in terms of percentage, or in terms of fraction, 0.5 A, 0.5 B. So in calculation, normally we will write this as YA naught, okay, equals to 0.5 equals to YB naught 0.5 as well. So let me make it bigger for you to see. So we need to say YB naught equals to YA naught equals to 0.5, the mole fraction. Okay, so next one, we know that enters the reactor at 343.15 Kelvin. So that's your inlet temperature. Okay, so T naught is 343.15 Kelvin. Okay, we do not know yet the reaction temperature. This is non-isothermal, but for now we know T naught is 343.15. And then this is 60 dm cube per second. So it enters the reactor at 60 dm cube per second. So dm cube is volume, second is time, volume per time is volumetric flow rate, and this is initial volumetric flow rate. So your epsilon naught is 60 dm cube per second. Initial concentration, A is 18.5. So this is Ca naught. So we know epsilon naught, you know Ca naught. Okay, done. This is assume work done by stirrer is negligible. Okay, so this is something new, but you know that this exists in your energy balance equation. Okay, your energy balance equation, we have this one terms, we call it as WS. So WS is work shaft, work done by the stirrer. So in this question, WS we assume as 0, as they say it is negligible. Okay, so next they say calculate the reaction temperature. So they want to know T. So I know T naught because it's isothermal, I have to determine T. When the conversion is given as 65%, so they give you the conversion. The conversion is 65%, or in terms of fraction, 0.65. Okay, next. They give you further information. So first of all, they give you steam jacket area, 18 dm cube square. So you know that when you have non-isothermal, when you are supplying heat to the reactor, you will have a heating jacket, okay, the outer vessel that provides the energy, the heat to the reactor. So whenever you see information regarding the jacket, you know that this is definitely to calculate Q, because the heat supplied to the reactor will come from the jacket. So this steam jacket area is technically your A in the equation to calculate Q. Overall heat transfer coefficient 23. This is your U, again is used to calculate the Q. Next, jacket steam saturation temperature. Okay, so this is basically TA, okay, the heating fluid inlet temperature that you will use to calculate again the Q value in the energy balance equation. Okay, it's 350 Kelvin. Next one, heat of reaction at reference temperature, of which the reference temperature is 273 Kelvin, and this heat of reaction is negative 70,000. Okay, meaning we have a reaction. The heat of the reaction at the reference temperature 273, meaning your TR is 273 and your heat of reaction is negative 70,000. And then next one, they give you constant heat capacity, CP. So you have CPA, CPB, and CPC. So you know that each compound, it has its own heat capacity at constant pressure, CP. So the value is as subsequently. Okay, so how do we solve this? So this is very straightforward, right? Okay, I know X. I know it's a non-isothermal. I want to find the reaction temperature. So of course, naturally, you will look at the heat energy balance equation first. So the energy balance equation, you can know is given as in the red font equation, right? So what we do is we have to find first one by one the values of each of the variables, and then we will substitute into the equation. Okay, so the first one, okay, Q. So since this is non-adiabatic, I will have to calculate Q. So the equation to calculate Q, so you know that calculating Q, you have a sub-equation. We have already learned. The sub-equation says Q equals to UA in bracket TA minus T. Okay, so you know your U is 23, your A is 18, your TA, your heat transfer fluid inlet temperature, or in this case, the jacket steam saturation temperature is 350, all right, minus T. T is the unknown that we want to find, so the T remains. Okay, so in my case, okay, when I want to solve equation of which you have a lot of brackets, you don't open the bracket first. Of course, there's no certain rules. Okay, of course it's free for you to open the bracket now. It doesn't matter. It's not wrong. However, to avoid the confusion in calculation, I will always ask my students not to open the bracket first. Okay, only open when it's necessary. So in this case, you can solve the front part. So the 23 and 18 you may multiply, but the bracket 350 minus T, if it's me, I will just leave it as it is first. Okay, so done for Q. So next, WS. Since the question says work done by stirrer is negligible, so you may leave the WS first. Leave. You can put WS as 0 because in simpler word, the value is too small in comparison to the other variables. So you may actually deem it as negligible as it will not have that much impact on your final answer. Okay, so next one is FA0. Okay, so FA0, you know, right? Initial molar flow rate of A. So if you realize in the question, okay, you can check. There are no information in terms of molar flow rate. You know that if it's FA0, the dimension must be mole per time. Okay, so you can see from the question, there are no information, numbers in terms of mole per time. However, you do know that we can find FA0 if we know CA0 and epsilon naught, meaning if I want to find molar flow rate, initial molar flow rate of A, if I know the initial concentration of A and I know volumetric flow rate, I can actually calculate it by multiplying CA0 and V0. So happen in this example, we know CA0 18.5 mole per dm cube and you know epsilon naught as 60 dm cube per second. So you can see, right, if we cancel the dm cube, you will get your final answer in mole per second, which is correct, molar flow rate. So you get your FA0 as 1110 mole per second, done on FA0. Okay, so next one, a summation. Theta I CPI. Okay, so if you forget, again, summation means plus, addition. You're adding something. Okay, summation is also means total. You're plus something. So what do you plus? Okay, so you know, it's addition of all the compounds that exist initially in the system before the reaction occurs. So how do I know this? Because we are calculating theta multiplied with Cp. So you know the concept of theta, right? We learn theta B, we learn theta I. Theta B is to refers to the initial amount of B over initial amount of A. So let's say you have inert, theta I, initial amount of inert over initial amount of A. So you know the meaning is all initial amount. So if you have reactant, you have to calculate. And of course, if you have inert, initially, you have to calculate as well. So in this question, in our reaction, we only have two reactants, A and B. There are no other compounds, there are no other inerts. So how do I know this? Because you can see in the questions, they do not mention any other species as this. So meaning, summation of theta I CPI will be equals to CPA, okay, heat capacity of A. Technically, as I always mention, to avoid confusion, technically it should be theta A CPA, but theta A is 1, so we do not write it out. So it's CPA plus theta B CPB. So theta B is not necessarily 1. Sebab tu kita kena tulis, theta B is not necessarily 1. So you write as plus theta B CPB. So then you calculate one by one. So CPA, you can check from the table, the heat capacity of A is 23. Done. Okay, what about theta B CPB? So now you have to calculate first theta B. Okay, how to calculate theta B? So theta B, the concept is the ratio of initial amount of B over A. So again, initial amount ni can be concentration, molar flow rate, can be mole fraction, depending on your question. So in this question, they give us the mole fraction, right? We know the initial mole fraction, we have 50% A, 50% B, meaning YA0 0.5, YB0 0.5. So theta B will be YB0 divided by YA0. So 0.5 divided by 0.5, you get 1. So theta B is 1. You multiply with CPB, which is 28, again from the table. Hence, you get summation theta I CPI as 51. So done on theta I CPI. Okay, summation of theta I CPI, sorry. So next, temperature. So T I want to find, so T I leave it as it is. T0 is the inlet temperature or the feed temperature, which is 343.15. So T0, 343.15. So let's go to the back. So again, FA0, we already know, we already solved FA0 initially. So it's the same FA0, so it's 1110. X is given in the question. X is, 65%. So X is 0.65. Done. Heat of reaction. In this question, we are very lucky. We are given the heat of reaction. So we don't need to calculate. So the heat reaction is given directly as negative 70,000. So we don't have to calculate. We can use it directly. So next one at the back, delta CP. Okay, so delta CP we have to calculate. So again, if you're confused about why sometimes we have addition, we have subtraction, you just focus on the mathematics symbol. Okay, delta means changes or differences. So when you have changes or differences, it means must be something that will be subtracted, something that will be added. Okay, so something will be positive, something will be negative. And in the concept of reaction, it's always positive for the product and negative for the reactant. So same concept applies. And again, let's say you're confused, okay, delta CP will have to include the ratio of the stoichiometric coefficient. So that means it is only calculated for all the compound that exist in the chemical equation. Meaning, if you have inert, you don't need to calculate the delta CP because the inert will not have the stoichiometric coefficient in the chemical equation because they are not involved in the reaction. Okay, so in this case, delta CP will be, since we have C as reactant, C as product, A and B is reactant. So C per A, the stoichiometric coefficient ratio, multiply with heat capacity of C, CPC, minus B per A, heat capacity of B, CPB. So why minus? Because B is a reactant, and minus heat capacity of A, CPA. Technically, it's minus A per A, but again, the same concept, A per A is 1, so we leave it. Okay, we do not write the A per A because it's understandable, it's 1. So just make sure you correctly refers to the right stoichiometric coefficient. Make sure you refer to the correct table of the CP value. You're able to get the delta CP as 25. So now I've obtained everything in my equation. So you may replace it finally into the final equation. So you have the Q 414 in bracket 350 minus T minus WS 0 minus FA0 1110. Okay, multiply with your summation theta I CPI, which is 51. Okay, in bracket T I want to find, so I leave it, minus T0 343.15 minus FA0 once more 1110, X 0.65 in bracket heat of reaction negative 70,000 plus delta CP 25 in bracket T minus TR. So T, I leave it. TR is 273. TR is a reference temperature. You can look in our equation. They have written in the question, they have written TR as 273 Kelvin. So when you do all this, don't forget it's equals to 0. Make sure you correctly solve this. This can be quite tricky, right? Because we have bracket, we have sub-bracket. But if you correctly do this, you will get the temperature, the outlet temperature or the reaction temperature as 999.18. I should write it is actually Kelvin. Okay, so we are done for question number 1. Question number 2, right? So question number 2 is as follows. Okay, you can see the questions. The endothermic liquid phase reaction E with 2B to produce C. Okay, so this says carry out in a single steam jacketed CSTR with an inlet temperature of 300 Kelvin, which rises to 600 Kelvin during the reaction. Okay, so you can see this is something different, right? The sentence. So first of all, dia adalah CSTR. Okay, second dia kata inlet temperature 300 Kelvin, meaning your T naught is 300 Kelvin. Okay, then it says rises to 600 Kelvin during the reaction, meaning okay, initially my T naught is 300 Kelvin, and then because it's non-isothermal, the temperature increased to 600 Kelvin during the reaction, meaning your T is 600 Kelvin. T naught 300, T 600. Okay, so this says for condition similar to those under which this CSTR operates, the reaction is first order with respect to A and first order with respect to B. So they give us the rate law. So the rate law says this is non-elementary. So the rate law minus RA equals to KCACB. So why KCACB? Because first order with respect to A and first order with respect to B. So they say assume the system is adiabatic and the work done by stirrer is negligible. Okay, so meaning to say adiabatic Q is 0, work done by stirrer negligible, WS is 0 as well. So Q 0, WS 0. Okay, so then they give us information, steam jacket area, overall heat transfer coefficient of jacket steam saturation temperature. Okay, so we know from question number 1 and from the lecture, these three information is to calculate Q. However, you must note, although they give you the values to calculate Q, but in this case, they say it's adiabatic, meaning Q is 0, or we can say that you don't actually need to calculate Q. So although the values are sometimes given in question, but not necessarily mean you have to use it to calculate. So this is an example where I have the value to calculate Q, but my Q is 0 because it is adiabatic. So done. So next one. They give us the feed flow rate. So you should know by now, right? The M cube per hour, volume per time. This is volumetric flow rate. So the epsilon naught is 20 dm cube per hour. Okay, so next they give us the value of K, but the value of K in terms of Arrhenius equation. So the K equals to A exponential minus EA per RT. So they give us in terms of Arrhenius equation for us to calculate the K. Alright, so done. So next one, they give us the table of information. So they give us the feed molar flow rate. So feed molar flow rate, you know, right? Mole per hour. This is molar flow rate initially. So they give us FA naught 15. FB naught 30. So why do we have FB naught as well? Because the reactant is A and B, and once more we don't have any inert. So there's only 2 reactant and 1 product. So FA naught 15, FB naught 30. So next one, they give us the enthalpy of formation. Okay, so enthalpy of formation A, enthalpy formation of B, enthalpy formation of C. So you should know, right? This enthalpy of formation will be used to calculate the heat of reaction. So as opposed to question number 1, in comparison, question number 1, they give us directly the heat of reaction. So you can use it directly. However, in this question, you are no longer given it directly. You can calculate it. That's why they give us the heat of formation that we can use to calculate the heat of reaction. So next one is we are given CP. So we have the CP of A, CP of B, CP of C. So naturally, we use this to calculate delta CP. All right, so done. So let us go to the question. So the question says, calculate the conversion of A in the reactor. So we are supposed to calculate X. So in this question, I know temperature. I know my outlet temperature or the reaction temperature T is 600 Kelvin. So I will use this to calculate X. So in comparison to question number 1, we know X, we find T. Question number 2, vice versa, we know T, we want to find X. Okay, so regardless, you will still use the same equation. So we have to then again find one by one. So in this question, Q is 0 because it is adiabatic. WS is also 0 because work done by stirrer is negligible in this question. Next one, FA0. So FA0 easy lah. We just see from the table. FA0 is 15. Done. Okay, so next one. Summation theta I CPI. So summation of theta I CPI is only for reactant and inert. We do not have inert as this in this question in the reaction. So we only have reactant A, reactant B. So summation theta I CPI will be equals to CPA plus theta B CPB. Okay, so CPA from the table, CPA is 51. So theta B, CPB. So theta B you have to find first. So in this question, the initial amount of A and B is given in terms of the initial molar flow rate because we know FA0 15, FB0 is 30 from the table. So we can use it to find theta B. So theta B equals to FB0 per FA0. So 30 divided by 15, you get 2. So theta B is 2. CPB is 44 from the question. So you get your summation theta I CPI as 139. Done. Okay, so next one. T minus T0. So you already know, right? T is 600 because the question already says the reaction is at 300 Kelvin and then rises to 600 Kelvin during the reaction. So T 600, T0 is 300. Okay, done. So we go to the back part. So FA0 again, 15 from the table. X we want to find. So the X now we leave it as it is. Okay, next, heat of reaction. So enthalpy of reaction. So similar concept. Enthalpy of reaction, you have the delta. So delta means differences. So it's going to be positive for product, negative for reactant, and you must include the stoichiometric coefficient ratio. That's why it becomes C per A, heat formation of C, minus B per A, heat formation of B, minus heat formation of A. Okay, so again, inert will not be included because naturally heat of reaction will not involve inert. And then second reason, which is the easiest one, you cannot find stoichiometric coefficient for inert from the chemical equation because they are not involved in the reaction. So that's why you want to calculate for A, B, and C. So you will get, do make sure you use the correct heat of formation. Do make sure you are aware of the negative signs as well if they have it. So in this case, the heat of reaction is negative 144,000. So next one, delta Cp. So similar understanding, just that delta Cp, you will use the heat capacity value. If heat of reaction just now, you use the heat of formation value. But the positive, negative, the stoichiometric coefficient ratio is still the same. So when you calculate it correctly, you will get delta Cp as negative 91.5. Okay, so similarly, after you have done all the sub-equation, now you can substitute into the main equation of which you're only left with one unknown, which is your x. So this, again, make sure you do it correctly, carefully when you want to open the bracket and so on. And you'll be able to get your x conversion as 0.24 or 24%. Okay, so let us go to the next part of the question, question B. So the question B says, determine the volume of the reactor. So they want us to find the volume of the CSTR. Okay, so to find the volume, you have to remember, this is what we learned in chapter 4, right? So we use information we get from part A and we have to apply what we learned in chapter 4. Okay, so to find the volume, the formula are very straightforward. Volume CSTR equals to FA0X per minus RA. Okay, then second, the rate law. So the rate law is already given in the question. They say first order with respect to A, first order with respect to B. So minus RA equals to KCA CB. Okay, so done. That next one. we have to express CA and CB first in the form of CA naught and conversion, because we do not know CA, we do not know CB, but we can find the correlation of CA in terms of CA naught and X, CB in the form of CA naught and X as well. So for this is a liquid phase reaction. So for liquid phase reaction, flow reactor, CA equals to CA naught in bracket 1 minus X, CB equals to CA naught in bracket theta B minus B per A X. So theta B we calculated in part A as 2. B per A is 2 as well. So you can see from the equation, right? B per A is 2 per 1. So that's why you get your CB in the form of CA naught in bracket 2 minus 2x, because theta B is 2, B per A is 2 per 1, so it's actually 2, right? So done. So now you combine equation 1, equation 2, equation 3. So you will get, okay, so the final equation you will get volume CSTR equals to FA naught X, bottom K at 600, because our reaction temperature at 600. So don't forget, for non-isothermal reaction, the K must be at your reaction temperature, not the inlet temperature. So the K must be at 600 Kelvin. So CA was CA naught 1 minus X, CB was CA naught in bracket 2 minus 2X. So you have to then substitute all the values inside the equation for us to find the volume. So first of all, FA naught. So FA naught. Okay, so FA naught in the question, of course, you know is 15 from the table. So FA naught is done. So you look at the final equation first. So FA naught done. Next one is X, right? So X is 0.24. From part A, we have solved the conversion. The conversion was 0.24 here in part A. So the X is 0.24. Done. So bottom, K as 600. So we have not yet found the K, right? Because K, although is given in the question, but it was given in the form of Arrhenius equation, of which we will use it to calculate the value of K. Since now we know the reaction temperature is 600 Kelvin. So you just substitute. So 10 is from the equation, right? So K 600 equals to 10 exponential minus 2000 calorie per mole divided by the gas constant 1.987, because this is calorie, and then multiply with your reaction temperature 600 Kelvin. So you will get your K as 600 as 1.8683. So K 1.8683. Next, CA naught. So CA naught in the question, we were not given. However, we were provided with FA naught and epsilon naught. Okay, so if I know molar flow rate, initial molar flow rate, I know initial volumetric flow rate, I can surely find the CA naught by dividing FA naught with epsilon naught. So I get 0.75. So done. CA naught, I'm done. X again is 0.24. So if you solve this correctly, you should be able to get the volume as 2.9654 dm cube per hour. So this is the answer for question number 2. Okay, so we will continue with the next question, question number 3. Right, so the question says normal butane, okay, and C4H10 is isomerized to isobutene, IC4H10. The reversible reaction is carried out non-adiabatically in the liquid phase. Okay, so the reaction is very simple, isomerization. So you know isomerization is still a chemical reaction. So we have 1A to produce 1B. Okay, so it's 2 different compounds. Right, so this says reversible reaction. So you have to be very careful because this is now reversible reaction. So previously we have only covered questions reaction of non-reversible, irreversible. So today, so question number 3 is slightly different. This is reversible reaction. So you have to remember what you learned in chapter 4. At the last part, we already taught you, we already learned about reversible reaction. So this is next. Carry out non-adiabatic. So non-adiabatic means we have to calculate the value of Q, Right, so this says you are tasked with determining the suitability of a steam jacketed CSTR with the inlet mixture of 90 mole% N-butene and 10 mole% isopentane, okay, and inert in the reaction. So, okay, so for this sentence, it's quite interesting. So first, CSTR. Second, information. Initially, although the reactant is normal butane, but it's not pure normal butane. They have another compound which is isopentane, of which this isopentane is an inert. So that's why you see it's only normal butane in the chemical reaction. There's no isopentane because isopentane is an inert, and as well as they give you the mole% initially. So normal butane, our A, the Ya0 is 0.9, and we have Yi0, the mole fraction of your inert, which is isopentane, 0.10. So we have Ya0, we have Yi0. We do not have Yb0 because initially only one reactant, one inert. We don't have B. Instead, B is now our product, which is isobutene, right? So they say additional information given below, assume work done by stirrer is negligible. So once more, Ws is 0. Okay, so they give us the first three information is to find Q, right? Steam jacket area, heat transfer coefficient of the jacket, jacket steam saturation temperature. Naturally, this one is to find Q. So next one, they give us initial flow rate of normal butane, which is 25 mole per hour. So this is FA0. Our normal butane is our A. So this is FA0, 25. So next one, they give us feed temperature, 300 Kelvin, T0, 300 Kelvin, equilibrium constant. So if you remember, we learned in chapter 4, we learned reversible reaction. We have this new unknown, we call it equilibrium constant, Kc. So Kc is 3. So this is definitely used to calculate later when we are addressing the reversible reaction. Okay, dalam energy balance equation tu got nothing to do with Kc, but perhaps later when we talk about designing the reactor, we will then use this Kc. So next one, they give us activation energy, EA lah. So you know EA definitely to calculate K from the Arrhenius equation. Okay, so next one, they give us enthalpy of formation. So again, kalau diberi enthalpy of formation, we will use it to find the heat of reaction. Okay, and the reference temperature is given as 273. So TR 273. And the second row, they give us CP. So CP for A, CP for B, CP for C. So this one is to find the delta CP, and then to find the summation theta I CPI pun kita akan guna this CP. So this says calculate the reactor temperature if the desired conversion of normal butane in the reactor is 60%. Okay, so they want us to find T when they give us the X as 0.6. So in this question, energy balance equation, I know X 0.6, I want to find T. So similarly, we will look at the energy balance equation once more. Okay, so again, this is a non-adiabatic. Kalau nak adiabatic, you have to calculate Q. So Q equals to UA in bracket TA minus T. So I know U, I know A, 12 and 10. I know TA, the jacket steam saturation temperature as 300 from the, jacket steam saturation temperature is actually 380. So this is wrong, right? So this one should be 380. All right, so jacket steam saturation temperature 380. All right, so T, I don't know. I want to find T. Okay, so there's a bit error. I have already corrected it. So this says WS work done by stirrer negligible. So no value. Okay, FA0 given in the question is 25. So we just put it as it is. We have to find summation theta I CPI. So in this case, this is quite different from the previous question because previous question you have reactant A, reactant B, no inert. In this question, I have only one reactant, but I have one inert, which is the isopentane, right? Isopentane, correct. So theta I CPI summation will be equals to CPA plus theta I CPI. So this I refers to the inert. Okay, so dalam case dia ada inert, so you have to calculate for the inert. So CPA is actually 0.40. Okay, so you can see this question, they beri untuk component A, component B, and they give for the inert as well. So you have to be very careful when you want to substitute the value. So CPA is 0.40. Okay, next one, theta I CPI. So we have to find theta I, which is the ratio of initial amount of inert over initial amount of A. So in this question, they do give us the mole fraction. They told us initially we got 90% A, 10% inert. So theta I will be equals to 0.1 divided by 0.9. Okay, so you get theta I as 0.111. So you will replace theta I 0.1111, and then you will replace the CP for inert. So the CP for inert in the second column, sorry. So it's 0.28. So we will replace 0.28. Hence, you get your theta I CPI at 0.4311. So we are done summation theta I CPI. So T, again, we want to find, we leave it. T naught is actually inlet temperature, feed temperature 300, right? So T naught is T naught is 300. Okay, so done. Right, so next one is the back part. FA naught is once more 25. X is 60%, so X 0.6. Okay, so next, heat of reaction. So heat of reaction, in this case, okay, we have to calculate using the heat of formation. So you only calculate for reactant and product. You don't need to include the inert again, because heat of reaction, inert is not involved in the reaction. So it becomes B per A multiplied with heat formation of B minus heat formation of A. So you can see in this example, the heat formation of B per A multiplied with enthalpy heat formation of B is positive, because in this example, B is a product. The previous example, B was a reactant, that's why you minus. This question, it becomes plus because B is a product. Okay, so then A is definitely negative minus lah, because A is always reactant. So make sure you check correctly the enthalpy of formation. You can see that this question somewhat trap you, because they give you the enthalpy formation of inert, although you don't actually use the value in calculation. So sometimes when you have certain value, make sure you really understand whether the value shall be included in the equation or not. Okay, so you will get the heat of reaction as negative 170, and similarly you calculate for delta Cp. So same concept, is only for reactant and product. You don't need to include inert in the calculation of your delta Cp. So you will get your delta Cp as negative 0.25. So once you have obtained everything, so TR is again 273. Okay, so that when you have already obtained everything, please make sure you solve it correctly. You will get the inlet temperature as 320.8715. So we are done on question A to find the temperature when you are given the conversion. So part B is determine the pre-exponential factor. So A, kalau pre-exponential factor to A in the Arrhenius equation. So you know definitely you will have to use Arrhenius equation to find the A. Okay, for the conversion and temperature obtained in part A above. So I can use the T in part A, I can use the X in part A if given the reactor volume as 25 dm cube. With initial concentration of A, the normal butane is the A, so as 2 mole per dm cube. The reaction obeys reversible elementary rate law. So this question is a bit difficult, right? They want us to find A. Okay, so they give us X, they give us temperature. They give us the reactor volume. So this example, it is a CSTR. So they give us the CSTR volume and they give us the CA naught. So V25 and Ca naught 2. They want us to find A, and they say reaction obeys reversible elementary rate law. Okay, so again, this question seems a bit tough because it's not so straightforward. We have a lot of information which we are not sure how to process. So I always tell advice, when you have this kind of engineering question, you always start with what they want to find. So they want to find A. So you know, if you want to find the pre-exponential A, definitely from the Arrhenius equation, for sure daripada Arrhenius equation. Okay, so let's say now you point out first the Arrhenius equation. So Arrhenius equation tu, you know, it must be K at 327.15. Kenapa K at 327.15? Because the temperature, the reaction temperature from part A we calculated was 327.15. So you know the K mestilah pada the reaction temperature. So okay, done. So this K, basically, we do not know. We know the temperature, but we do not know the value of K. So, kita merahkan dulu. We know that this is what we don't know yet. Okay. So, next one is A. So, A is what I want to find, right? So, A pun I don't know. Okay. So, A is also unknown. Okay. Activation energy, EA, they do give us, for the example, EA is 2 kilocalorie per mole, which is 2000 calorie per mole. So R I know as well, 1.987, and I know my temperature as well. So from this question, I know that they want us to find A, but I have one problem because I do not know the value of K yet. So meaning to say, in order for me to solve to get my A, I have to solve first the value of K. So now the problem is kita tak tahu value of K. However, you can see that they give us reactor volume. So you know that kan dalam design equation, which is to find reactor volume, we will have the K there because from the rate law kan the value of K. So meaning to say, if I can solve the design equation, I can actually get my K. Then from the K, I will replace in the Arrhenius equation to get my A. So the challenge now is how to find the K from the design equation. Bear in mind, this is reversible elementary rate law. So kita kena start from the very beginning. So first, design equation kata volume CSTR equals to FA naught X per minus RA. Then now kita cari rate law untuk this correction. So the rate law, you must understand, is not the same as irreversible. Ni reversible. So you check chapter 4 balik, how to write down the rate law. So nak tulis rate law tu pun ada dia punya rules according to the reaction. Because it says the rate law for reversible reaction equals to minus RA equals to K. So K at the reaction temperature, means temperature kita nak cari itu. Dalam bracket, the first term is the concentration of reactant, power stoichiometric coefficient. So in this example, is 1A produce 1B. That's why it's only Ca. Technically Ca power 1, tapi Ca power 1 is still Ca. So I just write Ca. Minus, next part, the top is concentration of products, all your products, power stoichiometric coefficient. In this question, there's only one product, which is B. So Cb power of 1. Okay, you don't write power 1, so it's okay. So you can just write it as Cb. So again, if you are cannot remember this part, please refer to chapter 4, the last part, how we write down the rate law when we have reversible reaction. Then divided by Kc. So Kc is the equilibrium constant, which we have already known from the reaction equation as, from the information as 3. Okay, so I already know my minus Ra. Then next, I have to express my Ca and Cb. So this is liquid phase flow reactor. So Ca equals to Ca naught in bracket 1 minus X. So you have to express again Ca. Then you have to express Cb. So in this example, Cb is a product. So if you're not too sure how to express it, please refer to chapter 3. But basically, Cb equals to B per A Ca naught X. Okay, if you're not sure how to express B, when B is a product, please check chapter 3, but it's actually equals to B per A Ca naught X. So B per A from the chemical equation is 1A, 1B. So B per A is 1 per 1 is 1, right? So we can write it as Ca naught X directly. Okay, so you have options. Okay, so first, you can combine equation 1, equation 2, equation 3. So when I combine it, I will get volume CSTR equals to FA naught X, okay, per minus RA, right? So equals to K in bracket, CA tadi CA kan, tapi CA in the form of CA naught in bracket 1 minus X minus CB. CB was CA naught X per KC. So this equation, by right, kita nak cari K. So the other unknown all you have to substitute with value in order for you to get K. So we know the volume is 25 dm cube. So volume CSTR 25 dm cube. FA naught is 25 mole per hour from the information. X is 0.6 from part A, the conversion. K I want to find. So let's say I put K as rate. That's something I want to find, right? So Ca naught is 2. Okay, so how we get the 2? Ca naught is given in, let me see, how do we get Ca naught? Ca naught is given from, hold on, how do we get Ca naught? Now this is a very, Ca naught is given in the question. In part 2 question they give us, Ca naught is 2. So Ca naught is already 2. So X 0.6, again you replace Kc3, equilibrium constant, and when you solve this, you will get the K as 1.5 per hour. Now that you have obtained the K, then only you substitute into the final equation of the Arrhenius, and then you'll be able to get your value of K, the pre-exponential factor, as 34.5486. So question number 3 is slightly complicated because first is a reversible non-isothermal reaction, and then you have to apply the knowledge of chapter 4 in order for you to express the Reed law for you to solve the question. Okay, so we have done question 1, 2, 3. So question 4, I will leave it as homework for you. As always, the questions are in the VLE and the teams, and the final answer is already given. So you can solve this by yourself. Please try to attempt question number 4 to test your understanding. And if you can solve question number 4, should not be a problem for you to understand tutorial chapter 6. So that's all for tutorial chapter 6. Okay, thank you everyone.